Hey everyone, welcome to the next Cosmic Adventure lecture. My name is Dr. Valerie Rapson and I am the director and astronomer at the Dudley Observatory. Today we're going to talk all about our star, the Sun. Now I know we've talked about our Sun and the solar system in the past, so today we're going to focus on some properties of our Sun that are linked to this brand new spacecraft called the Parker Solar Probe. Parker launched just a few years ago, and it's on its way to becoming the closest spacecraft to the Sun that we've ever been able to send out into space. We'll begin with a brief introduction to our Sun, both inside and out. Then we'll talk specifically about space weather, things like sunspots and solar flares, because that's really what the Parker Solar Probe is designed to study. Then we'll get into some of the details about Parker and share with you some of the latest results from one of its passes around the Sun. I always start a talk like this with a slide covering the basic parameters of our Sun so you can get a sense of just how big and hot and massive our Sun truly is. The diameter of our Sun is approximately 861,000 miles. That means it would take 109 Earths lined up end to end to cross the front face of our Sun. Its mass is about 2 times 10 to the 30 kilograms, so a 2 with 30 zeros after it. That's equivalent to about 330 times the mass of the Earth. So the Sun, being a star, is truly much, much larger than our Earth and much larger than any of the planets in our solar system. On average, the Sun is about 93 million miles from Earth. We do get a little closer or a little bit farther away as we orbit around the Sun, but on average, it's about 93 million miles away. Its composition, 73% hydrogen, 26% helium, and 1% other heavier elements, and that's composition by mass. So the Sun, as with most stars, are primarily hydrogen and helium, with a little bit of other elements like carbon, nitrogen, oxygen, iron, things like that. The brightness of our Sun, the total power output, I should say, 4 times 10 to the 26 watts. That's a 4 with 26 zeros after it. Now, these numbers are so huge that they're hard to comprehend, so another way to think about this, which may or may not help, 4 times 10 to the 26 watts is the equivalent of 100 trillion 40-watt light bulbs all turned on at exactly the same time. That is a ridiculous amount of brightness. Now, of course, our eyes don't see that total brightness at once here on Earth. The amount of light that actually reaches the Earth is far smaller than that because the Sun emits light in all directions, and as it travels through space, it also spreads out. So you'll see some numbers a little bit later on that talk more about the actual amount of power or brightness that we receive here at Earth. But that's the total power output of the Sun. Temperatures of the Sun, about 10,000 degrees Fahrenheit at the surface and about 27 million degrees Fahrenheit at the core. And overall, our Sun is somewhere between 4.5 to 5 billion years old, expected to survive at least for another 5 billion years. Then it will evolve to become a red giant and ultimately end its life in a phase we call a planetary nebula. So our Sun is a really interesting object. You can see a photograph of it there from one of our solar telescopes on the left-hand side. And basically, the properties of our Sun are very similar to other stars of the same size in the sky. Now let's take a look at the inside of the Sun. What would the Sun look like if we could literally slice it down the center and take a look at the different layers? Here we have a nice cartoon of what we think the inside of the Sun looks like. The Sun is split up into 3 layers. We have the core at the center, the radiative zone outside of that, and then the top layer of the Sun is the convective zone. Each one of these layers fills about 1/3 of the Sun. So the inner 1/3 of the Sun is the core, the next 1/3 of the Sun is the radiative zone, and then the final 1/3 is the convective zone, all the way up to the photosphere, which is technically the solar surface. Each layer has a different function inside of the Sun. The core is where all of the exciting stuff is happening. The core is where we're fusing hydrogen into helium, and the sun is making its energy. It's only the core of a star that experiences fusion, not the entire star, just the material in the core, because the core is the only place that is hot enough for this fusion to actually happen. So our sun is actively fusing hydrogen into helium in its core. The next layer, the radiative zone, that's where the light energy is transferred by bouncing around and constantly being absorbed and re-emitted by the different bits of plasma that are in the sun. So you have the light and the energy that is produced in the core. It travels through the radiative zone by bouncing around all over the place, ultimately reaching the bottom of the convective zone. Once that energy reaches the convective zone, it is carried up to the surface via convection. Convection is exactly what happens when you boil a pot of water on the stove. You heat the bottom of the pot, the water starts to bubble and boil, the motion of the water transfers the heat energy through the entire pot, and you've got a nice hot pot of water to make your pasta on the stove. The convective zone is doing exactly that, not making pasta, but transferring that energy all the way up to the solar surface. So when the radiative zone ends, the energy reaches the bottom of the convective zone, and the plasma lifts that light and that energy to the surface, where it's ultimately released into space at the photosphere. Just above the photosphere, so now we're talking outside of the sun, we have the chromosphere. It's a very thin layer just above the solar surface, and it's quite warm. That's where most of the ultraviolet light is created for the sun. So the reason that you have to wear sunscreen on a sunny day is because the chromosphere is making that UV light that ultimately reaches the surface of Earth. So you can thank the chromosphere for that. Above the chromosphere, the final layer of the sun, exterior to the sun, is the solar corona. You can think of this as a large atmosphere around the sun. It actually extends many millions of miles above the solar surface. It's incredibly thin, but it's also very, very hot. And it's these exterior layers, things like the chromosphere, the corona, and the resulting space weather, things like solar prominences and flares. That's what we're going to focus on in today's lesson, because that is the type of stuff that the Parker Solar Probe is planning to study. All right, so we've learned about the basics of our sun. Now let's talk specifically about solar activity. That is things that are changing on the surface of the sun and the space weather that it ultimately creates. Our sun is constantly changing. If you were to look at the sun today safely with a telescope, it would look very different than it did yesterday, and tomorrow things will likely be very different as well. Thankfully, we have these types of solar telescopes that allow us to monitor the sun day to day, year to year, and we constantly see these changes. You can see an example of this in the picture here. We have an image of the sun in May of 2010, and then going around the circle, September, March of 2011, September, March of 2012, and then September of 2012. And in each picture, the sun looks very different. Sometimes you see bright spots, those would be sunspots. Sometimes you see what looks like material coming off the surface, those could be solar flares or solar wind. All of this type of stuff is constantly happening on the surface of the sun. And it's very important that we study it in an attempt to be able to predict it. Because as you might imagine, things like solar flares and solar wind, which are plasma traveling at very high speeds to the Earth, they can actually cause damage to our satellites and even put our astronauts in danger. So we really want to be able to understand how it works and also attempt to predict this space weather. That's really what many of our space and ground-based solar telescopes are focusing on now. How can we understand and predict this solar weather a little bit better? One thing that's very helpful to try and understand is what causes the solar activity. Because if you don't understand the root cause of the activity, then you're probably not going to be able to predict that solar activity very well. Right now, we believe that the solar activity is caused by moving, twisting, and breaking of magnetic field lines near the surface of the sun. So let's break this down a little bit. We know that our Earth has a magnetic field, basically a shield around it caused by the fact that we have a molten iron core that's constantly churning and moving, generating this magnetic field. The sun does not have a liquid iron core, but rather the solar plasma is so hot that it's ionized, meaning the individual hydrogen and helium atoms have lost their electrons. The electrons are free floating, and the nuclei of the atoms, those protons and neutrons, they are bound together just to be the nucleus of the atom, but they're floating independently of the electrons. And when you have free-floating electrons, these negatively charged particles, if they're constantly moving, then you can create a magnetic field. So we think that somewhere deep inside of the sun, this motion of plasma, it's constantly churning and moving, just like the interior of our Earth, that is what is creating this magnetic field that surrounds the entire sun. You can think of it as if the sun has a giant bar magnet on the inside with a north and south pole, and the magnetic field then goes through the sun and extends out above and around the sun and re-enters on the other side. That is the very basic explanation of what's happening in the sun, and ultimately this magnetic field is what's causing the solar activity. When the magnetic field lines get twisted up, when they break, that's what triggers things like sunspots and flares. Now, exactly where the field is generated is actually a mystery, meaning it doesn't actually have to be generated at the core, at the center of the sun. In fact, it might be generated at a higher level. So we don't exactly know where the bar magnet is, basically, or how high up and down it extends. All we can tell is that there is a magnetic field present that surrounds the entire sun, and it seems to be triggering all of this solar activity. But exactly all those nitty-gritty physics-based details of how it occurs inside of the sun and where it occurs inside of the sun is still a little bit of a mystery. But that's the basic idea. So now that we've said, solar activity is created by magnetic fields, let's take a look at some specific types of solar activity and space weather and see how it links back to magnetic fields, look at what we know, and look at what we have left to understand. We'll start with sunspots. They're the most basic type of solar activity, and many people have actually safely observed sunspots. If you have the opportunity to look through a specially designed telescope that it can point at the sun safely, you can often see sunspots, these dark spots that happen all over the surface of the sun. Sunspots were observed as far back as 800 BC. Now, this was long before the telescope was invented, so people must have actually been directly staring at the sun at that time to be able to see these spots. It was recorded, sunspots were recorded, I should say, as soon as the telescope was invented. Once we realized that we could point the telescope at Jupiter and Saturn and see the rings and the moons, we decided to point the telescope at the sun, and then the sunspots really became apparent. With modern day telescopes, we can see sunspots in much more detail. The photograph at the bottom here shows you an example of some sunspots on the surface of the sun. Now, these spots, what are they? They are actually places where the magnetic field is leaving the sun, and they appear dark on the surface of the sun because they are cooler. If you could measure the temperature of any one of these little black dots, you would find that the sunspot is around 6,000 degrees Fahrenheit, where the exterior of the rest of the sun is around 10,000 degrees Fahrenheit. So that temperature difference of a few thousand degrees makes it such that the spots appear dark, even though they're still emitting tons and tons of light, because you're comparing them to a piece of material right next to it that is emitting far greater amounts of light at much higher temperatures. So the fact that these are little cold spots is why they look dark on the surface of the sun. Let me show you a picture of the sun here to give you a sense of scale. Just how big are these sunspots on the sun? Here's a great image of the sun back in October of 2014. The big yellow ball is the sun, and these 4 regions that are labeled with numbers here are actual sunspots on the surface. We have superimposed the size of Jupiter and the size of planet Earth onto the sun so you can get a sense of scale. These small individual sunspots are about the size of Earth, and this large sunspot group here is actually about the size of Jupiter. So what we're really looking at with these spots are almost holes or regions where the material on the surface of the sun is much cooler, and these regions are the size of entire planets. They are absolutely huge. They just look so small because the sun itself is so big. So when you're comparing the spots to the sun, they look small, but in reality, these are spots on the sun that are as big as planets in our solar system. So I mentioned that magnetic fields are to blame, right? Magnetic fields are what's causing these sunspots. So what exactly is happening? Well, we know that the magnetic field is generated somewhere in the interior of the sun, and it doesn't really matter where at this point, but it's generated somewhere in the interior of the sun. And the magnetic field then travels to the surface, and it turns out that sunspots are actually places where the magnetic field is exiting the sun, looping up into space, and then re-entering. Sunspots will often appear in pairs where you've got one sunspot where the magnetic field is exiting the sun and another spot where that same piece of magnetic field is re-entering the sun. You can see a pair of large sunspots in the upper right and a cartoon of what we think is happening on the bottom here. So these red lines are representing magnetic field lines coming out of the sun and going back in. Now, why does it generate spots? Why do we get dark spots on the sun? Well, when the magnetic field travels up and out of the sun, what it's doing is it's prohibiting convection. The surface of the sun is always convecting. It's always trying to mix the plasma together and make the entire sun the same brightness. But when the magnetic field exits the sun at these spots, it's actually stopping the convection from mixing the plasma together in that small region. So what you end up with is plasma that is colder on the surface because you're not efficiently transferring heat via convection into that region, and you create a spot. A small, sometimes we'll call it a small magnetic storm, but it's really a region where the material is not getting mixed efficiently, and therefore it's slowly cooling off. So these magnetic field lines, they'll exit out, they'll create a cooling region, they'll loop up high, and then they'll re-enter the sun here, and then go deep back down into the sun, again prohibiting convection in that second sunspot area. We know this because we actually can look at these sunspots with spectra, these devices that can break up the light into its constituent colors, and we can actually see the magnetic field affecting the absorption lines. Basically, the plasma is absorbing light at very specific colors, and we actually see these lines split because of the magnetic field. We can talk about that in more detail sometime if you like, but basically we have proof that these sunspots are caused by the magnetic field exiting and entering the sun, prohibiting convection from churning up the entire solar surface. Now, when sunspots appear, we often see prominences that go with them. If the magnetic field is exiting the sun, these field lines, they'll travel up high into space and come back down. Remember that there is a layer above the surface. There's a chromosphere and a corona. It's a lot thinner, a lot less dense than the sun itself, but there is plasma there. When the magnetic field lines leave the solar surface, they will often trap some of this plasma and create a solar prominence. Here are two pictures, examples of solar prominences. These are real photographs of the sun. On the left, you can see a solar prominence here, really big loop of plasma caught in some magnetic field lines coming out of the sun. And same thing on the right-hand side. And on the right-hand side, you can see, if you look very closely, you can even spot the sunspots here, the little dark regions on the surface of the sun where the plasma is entering and exiting the sun. But anytime this plasma gets trapped in these field lines, it'll create a prominence. And the prominence can actually rise really high. It can go 60,000 miles above the solar surface. So the plasma can go really high above the surface and then loop on back down. This is really cool to see. Now these prominences and sunspots, they don't last forever. They generally last only a few weeks and sometimes as short as just a few days. What happens is the magnetic field that's connecting the spots and causing these prominences to happen, the magnetic field will either weaken and just kind of go away and the prominence will dissipate, or the magnetic field lines will get twisted up because the plasma is always moving, and they will break. And then the prominence will split, the material will fall back down under the surface of the sun, and then the sunspots will go away. Convection will be able to mix up that plasma again, and it will bring it back up to the correct temperature for the surface of the sun. Here we have two more examples of solar prominences. The one on the left is just a really neat picture. Look at the lines. You can really see the plasma tracing magnetic field lines. Think back to high school if you ever did that experiment where you sprinkled iron filings over a magnet and you saw the magnetic field lines. That's essentially what we're doing here, except the solar plasma is acting as the iron filings. It's getting caught in those lines, allowing us to directly see them. So cool. And on the right-hand side, we're seeing a solar prominence actually about to break. So notice that the plasma is coming out and going back in. And it's not really a distinct loop. It looks kind of twisted and torn up at the bottom there. That's because the magnetic field literally is twisting up and it's breaking. And when it officially breaks, the plasma is going to retreat back down onto the sun in both directions. And again, the sunspot will get mixed back up and it will go away. Now, occasionally, when that magnetic field breaks, you don't have the plasma just delicately fall back down onto the surface of the sun. It will actually get released into outer space. This is what we call a solar flare. So you're seeing a video of a real solar flare at the bottom here. You initially see that loop, that prominence. Then the magnetic field line breaks, which you don't really see that too distinctly. You just see the plasma flying away towards the left-hand side of the screen. So in this case, everything was so powerful that the plasma was actually carried away from the sun in the form of solar flares. Now, when this happens, we often get a burst of X-rays and other charged particles that get hurtled towards the outer solar system. And if these flares are aimed directly at Earth, that's when they can cause real damage, right? If we get directly hit by a solar flare, we're in trouble. Thankfully, the Earth has a magnetic field of its own that protects us from some of this stuff, but a strong solar flare can overpower that, and again, it can cause a danger to our satellites, and it can cause a danger to any astronauts that are on the space station, or any astronauts that are doing any kind of future space travel that we hope to happen. So trying to understand these flares a bit better and being able to predict when they're going to happen is definitely a key thing that astronomers are looking into. We talked about the solar activity that happens on the surface of the sun. Now let's move to the solar corona, the sun's atmosphere. The solar corona is a very thin plasma-filled atmosphere that surrounds the sun. Recall that it goes a couple million miles above the solar surface. And it's incredibly hot. It's over 1 million degrees, which is way hotter than the solar surface. And this is very strange. This is not something astronomers expected. The density of the solar corona is very low. And you would expect that if you have hot plasma, even if it came from the sun, at such low density, the temperature should be far lower than the surface of the sun, which has much higher density. To give you a sense of scale, the average density of the solar corona is about 10 to the minus 16 grams per cubic centimeter. That's a decimal point with 15 zeros and then the number 1. That's how many grams per cubic centimeter the solar corona plasma is. Air density on Earth is 10 to the minus 3, so 0.001 grams per cubic centimeter. The air around us is far more dense than the solar corona. But somehow it stays really, really hot. And we just don't know why. That's one of the biggest mysteries of our sun that astronomers are trying to figure out. We know that most solar activity, including the stuff that we see in the corona, is probably caused by magnetic fields. But exactly how magnetic fields carry plasma to the corona and allow it to remain so hot is still a mystery. You can see a couple beautiful pictures of the corona at the bottom of the screen here. Seeing the solar corona requires either special instrumentation or a solar eclipse because the brightness of the actual sun is going to outshine any material you'd see in the corona. But here we have two pictures taken during the solar eclipse. So the sun is actually behind the big black circle, which in both of these pictures is actually the moon. They've just darkened it out completely so you don't see any features of the moon. And all of this white material that you see on the outside of each photo, that is the solar corona, the superheated plasma that is surrounding the outside of the sun. Now, since the corona is so hot, it actually emits not at visible wavelengths of light, but at X-ray wavelengths. The hotter the material, the higher energy light it's going to naturally emit. So if you have an object that's at 1,000,000 degrees Fahrenheit or even 1,000,000 degrees Kelvin, because at that high temperature, Kelvin and Fahrenheit are pretty much the same. If you have an object at that high temperature, it's going to naturally emit X-ray light. So we can actually look at the sun with specialized X-ray telescopes to try and learn a bit more about the corona. That's what you see on the right-hand side. So this is a photograph of our sun, but it's taken not with a regular telescope, but with an X-ray telescope. So what you're seeing in the background, there's like a dark circle. That is our sun. And it looks mostly dark on the surface because the surface of the sun is not hot enough to emit X-rays. Remember, it's only the corona, the outer atmosphere, that's hot enough to emit X-rays. So no X-rays is going to look dark in this picture. The loops that you see kind of all around the center of the sun here, that is material that is in the corona around the sun. And the fact that it has that loopy structure, it kind of looks like a whole bunch of prominences coming out of the sun. That is what clues us into this idea that it must be the magnetic field carrying plasma into the corona, causing it to heat up and get this hot. If there was some other function, we wouldn't see these loops, right? We're literally seeing prominences travel up into the solar corona, and somehow it's getting the material so hot that it's emitting at X-ray wavelengths. So we're literally seeing the connecting magnetic field lines to spots coming out into the corona, and then the material traveling back down to the surface of the sun. So again, exactly how this works is still a bit mysterious, but when we look at pictures like this, we get clues that it must be the magnetic field that is doing this in some way. Now, to go back to these dark regions for just a second, If you look at the top and the bottom, it looks like the northern and southern regions of the sun are very, very dark. And as we said, these are regions where we're not seeing any X-ray light. We're seeing the surface of the sun, which is going to look dark in these types of pictures. What this is really telling us, though, is that the corona is primarily filled with hot plasma near the equator, near the middle of the sun, and the northern and southern regions of the sun are more devoid of coronal gas. There's not as high of a density of plasma in the corona near the top and the bottom. So we call these coronal holes, and we're able to see the coronal holes in X-ray because, again, they're going to look dark in pictures like this. This all kind of makes sense because when we match sunspot position with what we see in these pictures, we find that sunspots tend to occur closer to the solar equator. Very rarely do they occur at the very top or bottom of the sun. And if it truly, again, is magnetic fields carrying the solar plasma up into the corona and heating it, we would expect to see the hottest material near the region of the sun where the sunspots tend to be. And that's exactly what we see here. Sunspots near the equator, and therefore hotter coronal plasma at the equator. Near these coronal holes, we don't see as much plasma, not as many sunspots, and the magnetic field is not looping and connecting the plasma into the sun in these regions. Connected to the solar corona, we also have the solar wind. The solar wind is literally a stream of charged particles flying away from the sun and out to the edges of our solar system. This wind was theorized by Dr. Eugene Parker in 1958 and officially confirmed by Soviet and NASA spacecrafts in 1959 and 1962. The bottom picture here you can see is actually an illustration of what the solar wind might look like. So we've got a cartoon white circle for the sun. You've got these big loops here. Those are our prominences and the magnetic field carrying plasma up to the corona. And then these white lines here and the little dots that you see streaming away into outer space, that is literally the solar wind. These charged particles that seem to be emanating out from the sun in all directions. Dr. Parker theorized that this must exist, and they were discovered shortly thereafterwards. Now our current spacecrafts are trying to discover exactly what is the solar wind made of and how exactly does it travel. You'll see in a little bit that that's one of the key things that the Parker Solar Probe, now you see where the name came from, is really trying to discover. It's trying to understand more about the process of this solar wind. So what do we know already about the solar wind? Well, as we said, we know it's a stream of charged particles, primarily ionized hydrogen, which would just be protons then, traveling out from the sun in all directions at up to 1,000,000 miles per hour sometimes. So somehow the sun is tossing out this plasma into outer space at incredibly high speeds. That's another mystery. How does it get the solar wind traveling so fast? Now, when we look at the sun, we find that the solar wind primarily exits the sun through the coronal holes. And you can see that in these pictures. So on the left, we just have an example of a coronal hole. So you can see this is a little video of the sun turning in time. That is an X-ray image of the sun. So you've got the dark region here, that's a coronal hole. If you look at the picture on the right-hand side, this is a composite image where we've taken a real photograph of the sun and put it on top of a real photograph of the solar corona and the solar wind. So two images that we've just overlaid, because in reality, you can't see the corona and the sun at the same time. But when we look at this picture, we can see some really bright regions. Those are the prominences that are coming up and heating the solar corona. And then all of these white lines that you see moving outward, especially in the northern and southern parts of the sun, that is the solar wind that is exiting the sun. As we said, it seems to come out of the sun in all directions, but it seems to be a bit stronger leaving the sun out these coronal holes, right? So you see the straight lines out the northern and southern hemispheres, whereas right near the solar equator, you've got some more prominences and loops heating the corona. But indeed, the solar plasma is tossed out at all locations and in all directions. So how do these particles get tossed out, and how do they gain such speed as they're traveling through outer space? That is an open question that we have yet to answer. All right, so you guys are now experts on space weather and solar activity. You know about sunspots, you understand the corona and the solar wind. Now let's switch gears just a little bit and talk about this new spacecraft, the Parker Solar Probe. Parker launched back in August of 2018, and it's literally, as the logo says, a mission to touch the sun. It's going to get within 4 million miles of the solar surface, which means it'll be directly entering the corona, and that's closer than we've ever been able to send a spacecraft to the sun before. So Parker is really a unique spacecraft, and we're going to talk in a few minutes about how it can actually withstand getting that close to the sun. What are the goals of the mission? Well, you'll see some common themes emerging that we've already discussed here. First, we want to determine why is the corona so hot, right? How exactly does the sun and the magnetic field transfer the energy to the corona to keep that plasma so darn hot? We also want to know more about the solar wind. What is it made of, and how does it get to travel at such high speeds? What mechanism is accelerating these particles? And then finally, we just want to know more about the magnetic field overall. If we can get close to the source, right? If we can get as close to the sun as possible, then we can really measure the strength and the direction of the magnetic field. And maybe that will allow us to understand the physics better that ultimately causes and creates all of the solar activity that we've just talked about. So that is really the goals of the Parker Solar Probe. And this is the first spacecraft of its kind. We've never designed a spacecraft that can get this close to the sun and that can study all of these types of things at once. Let's take a look at some of the instruments on the Parker Solar Probe that's going to help us answer these questions. There are 4 main instruments. You've got WHISPER, the Wide Field Visible Light Imager. You've got the fields, antenna, and magnetometers, the ISIS suite, and then the SWEEP instrument, the solar wind, electrons, protons, and alpha particles instrument. So what does each of these do? Well, the simplest one is WHISPER, right? It's literally a wide field visible light imager. It's literally a camera. Its goal is to take pictures of the sun, to take pictures of the solar corona where possible, and just give us some images that we can look at of the sun to see what's going on. The fields, antennas, and magnetometers are designed to actually study the magnetic field. We want to be able to detect the strength and the direction of the fields that are emanating from the sun, again, to give us more clues of exactly how they work. The ISIS suite is a couple of instruments that are actually particle detectors. So this set of instrument is literally detecting the individual particles. So what is the solar wind made of? And a bit of the properties of it. So how much of the solar wind is hydrogen versus helium nuclei or other elements that we might be finding there? And what are the properties of those atoms as they travel by, or those nuclei as they travel by the spacecraft? And then SWEEP is a similar instrument. It is also a particle detector, but its real goal is to look at everything, electrons, protons, nuclei, whatever, and measure speed, density, direction. So SWEEP focuses more on the properties of the solar wind, as in, how it's moving and what direction. And the ISIS suite focuses a little bit more on what the solar wind is made of. So by combining all of this information, we're going to hopefully be able to answer those questions that we brought up before. Learn more about the solar wind, the magnetic fields, and actually get a direct view from inside of the corona. There's also solar arrays to help power the spacecraft and a thermal protection system on the front to protect the spacecraft from all the heat that you might imagine it will experience when it gets to within only 4 million miles of the surface of the sun. How is Parker going to get there? Well, remember that the sun is on average 93 million miles from Earth. And it's not as simple as just launching a spacecraft and sending it directly to the sun. If we do that, the sun's gravity is so strong that it will likely get caught in the gravitational field of the sun, spiral around a few times, and then fall in. That's not what we want here. We want to be able to loop around the sun and get very, very close without falling into the star. So how do we do that? Well, we actually use Venus as our assistant. So in our cartoon here, we've got Earth, we've got Venus, and we've got the sun. This is horribly not to scale, size, distance-wise, or any of that, but we'll use the cartoon anyways. So basically what happens is you launch your spacecraft from the Earth, you fly by Venus and use Venus as a gravity assist, meaning the gravity of Venus tugs on the spacecraft slightly and kind of aims it towards the sun. Once you fly by Venus, you loop around the back of the sun, come back towards Earth, but you don't come back all the way to Earth. You come back as far as Venus and you loop around again. Venus and then the sun, then you loop around again and again. And each time you go around Venus and the sun, you're using both the star and the planet as gravity assist devices. You're using their gravity to kind of narrow you in closer and closer and closer until ultimately the spacecraft will be able to get within that 4 million miles of the sun and then orbit directly around the sun a whole bunch of times. So we need to go in slowly, again, using Venus as our assistant to slowly loop us into the sun so that the spacecraft doesn't just immediately fall in. As of 2020, when we're doing this presentation, Parker had completed its 5th close pass of the sun, so it's going to loop around the sun and Venus 7 times, and then it should be able to be close enough to the sun to orbit and get within that 4 million mile range. So what's it going to look like for Parker when it actually gets to the corona? Here's a nice slide that compares, basic conditions that it would experience at launch on Earth to the conditions that it will experience once it's within the solar corona. On Earth, things aren't that bad, right? Temperatures of up to 130 degrees Fahrenheit at launch. It can get pretty toasty in the rocket. Radiation levels, 1366 watts per meter cube. Remember early on we talked about the power the sun emits, how much wattage the sun has. This is the amount of radiation that actually makes it to Earth, about 1400 watts per meter squared on the surface of the Earth. So not that much solar radiation. Speed of the spacecraft is going to be about 18,000 miles per hour when it leaves the Earth. And then once it gets to the sun, things are going to go way higher, right? All of these numbers are going to get crazy high. So when Parker is within the corona, it will experience temperatures anywhere from, about 1,000 degrees Fahrenheit all the way up to 3.5 million degrees Fahrenheit. Really, really high temperatures. Radiation levels of 649,000 watts per meter squared, so a lot more light beating down on it. And speeds, it's actually going to break the record for being the fastest traveling spacecraft at over 450,000 miles per hour. Now, I know what you're thinking. Those are some high temperatures and high radiation levels. How in the world is this spacecraft not going to melt, right? How are we not going to get this thing to the sun and then not have it melt into a puddle of goo that then falls into the star? Well, there's a couple of things that we've done to prevent this from happening. There's the engineering side, which I'll show you in a moment. There's actually a protective shield on the spacecraft. But we also have to remember that there's a difference between the temperature and the heat that we feel because of the density of the material. So think about being in the kitchen again. We talked about, boiling our pot of water on the stove for convection earlier. If you stuck your arm inside that boiling pot of water that's over 200 degrees Fahrenheit, you would burn your hand, right? You would scald your hand. That would not be a good idea. But every day you bake things in the oven, which is 350, 400, maybe even 500 degrees Fahrenheit. You open the door and you stick your arm in a 500-degree oven, and hopefully you don't burn yourself. The temperatures are higher, but the key difference is density, right? There's a lower density of air inside of your oven, and that makes it safe to put your arm in the oven for a short period of time to take out your food. The density is much higher in that boiling pot of water, so you're going to scald yourself very quickly. The corona is incredibly hot, millions of degrees Fahrenheit, but remember that density is very, very low. So Parker flying through the corona, even though those individual particles are at incredibly high temperatures, there's not a lot of them. So Parker's going to be able to withstand this heat purely because of the low density environment. Now that doesn't mean that we should send the Parker Solar Probe without some sort of protection, right? Those temperatures and radiation levels are going to be really high. So the front of the spacecraft that is going to be pointed at the sun actually has a very specialized shield. You can see it on the cartoon here, and the colors are representing different layers of this heat shield that will allow the spacecraft to withstand temperatures of up to 2,500 degrees Fahrenheit. If you look at the image on the right, this is the different layers. You've got a white ceramic coating on the very outside, literally white to reflect back some of that heat and energy. And then on the inside, you have carbon-carbon and carbon foam. This material is very, very efficient at dissipating heat. There's actually some really cool videos you can look up yourself where they take a blowtorch to this material and they have someone put their hand behind the material and then they hit it with a blowtorch to show that this material will withstand that heat and the person touching the back of the material won't feel the blowtorch at all. So Parker is going to be protected and it's going to always be aiming that heat shield towards the sun so that the rest of the spacecraft will be protected and hopefully it won't melt. So far, it's done pretty well at not melting. So Parker has been traveling towards the sun for the last couple of years, and it hasn't arrived at its final destination yet, but it has gotten within 15 million miles of the sun, which is pretty close, and it's actually sent back a couple of interesting results already. So let's take a look at them. One of the things that we wanted to understand about the solar wind was not just its speed, but also its direction. Our current knowledge and our measurements based on what we can take from here on Earth suggested that the solar wind was literally released by the sun straight out, meaning pick any spot on the sun and the magnetic field was releasing that solar wind straight out from the sun. You can see that in this, again, horribly not to scale basic cartoon, where you've got the sun here, you've got a solar flare and some solar wind literally coming straight out of the sun, and sometimes it will hit the Earth and get deflected around Earth's magnetic field. But the direction of the solar wind seemed to be coming, directly from the sun. We weren't getting solar wind at an angle. It was always coming straight at Earth, so we imagined that it was going straight out into outer space at all directions. But what Parker found was actually a little bit different. We do see the solar wind emanating out in all directions, but it exhibits something we call a switchback. So the Fields instrument on the Parker Solar Probe actually detected a flip in the magnetic field very briefly, which disrupted the outward motion of the solar wind. So what would this actually look like? The picture here is not a real photograph. This is a cartoon of what the detectors have found. Here's your sun, and these little spikes are representing the solar wind traveling outward. In our previous model, everything would travel straight outward. From whatever spot, it would go straight out into outer space. But look here in the cartoon, you can see that there's these little S shapes, these zigzags. These are the switchbacks. Apparently, the magnetic field that helps carry and push the solar wind outward literally flips. So the north end becomes the south end. It flips for a brief time, causing the magnetic field, or excuse me, causing the solar wind to backtrack on itself and then go back out and travel through outer space. These switchbacks, these flipping of the magnetic fields, they can last from a few minutes to a few hours, and they occur in all directions, meaning it doesn't seem to be that like only in the direction of Earth do they happen. They seem to happen all around the sun. So what the heck is causing these, right? What is the origin of these switchbacks? What is happening inside of the sun that triggers this? We don't know. That's still an open question. And are these switchbacks things that emanate from the sun, or do they just happen at a certain distance? So what I mean is, if we go back to our cartoon, the little zigzag here, did the zigzag, start at the surface of the sun and get carried outward? So we would imagine that this little zigzag would travel out into outer space continuously? Or is it at this distance, whatever this distance is from the sun, where the switchback occurs, and then the individual solar wind particles will then continue to travel outward straight? We never saw these before by measuring these particles at Earth. So these switchbacks clearly only happen much, much closer to the sun. And by the time the solar wind reaches the Earth, the switchbacks are nowhere to be found. These are interesting because these might give us clues as to how we are accelerating the solar wind, right? If the magnetic field is flip-flopping, this might somehow give the solar wind a push. So we don't have all the details yet, but these are pretty neat. We never expected to find these. And as Parker gets even closer, we'll have more information about these switchbacks and see if they actually emanate from closer to the sun or if they seem to only exist further out. Another cool thing that the Parker Solar Probe is looking at is dust around the sun. Now, I know we didn't talk about dust and space weather because the dust really isn't linked to the space weather, but the presence of the dust around the sun sort of is. So basically, our solar system naturally contains little dust particles. These are literally leftover bits of the early solar system. When we were forming planets, a majority of the dust and the gas in our solar system got collected into the planets, and much of it then fell into the sun. But there is a faint dust that permeates through the whole solar system. We call it the zodiacal dust, and it's just those little leftover bits of the dust in the air. You can see it if you use a proper telescope. This is a neat image taken from Earth of the night sky, and this triangular glow here is actually sunlight bouncing off of dust particles in our solar system. So we can see the zodiacal dust from Earth. We know it exists, and it's been around for the last 4.5 billion years. Now, what does this have to do with the sun? Well, it was theorized that this dust, if it happened to be close to the sun, it would get vaporized, purely because of the strong heat and radiation levels from the sun. It would vaporize this dust, turn it into a gas. But we've never gotten close enough to the sun physically to see if the dust actually is vaporized. That's what Parker is going to give us some clues on. So even though Parker has not gotten to that 4 million mile distance yet, it has been able to look towards the sun and already suggest that there actually is a dust depletion zone. The bottom picture here is a cartoon showing the sun. The zodiacal dust is represented by this brown glow here. And then you've got this inner dark ring that seems to be devoid of this dust. And we think about 7 million miles out from the sun and closer, the sun indeed vaporizes this material. Our basic measurements of the amount of material around the spacecraft at that distance suggests that there is a dust depletion zone near the sun. So this is kind of an interesting result. It confirms some basic physics that we thought we understood about the solar system, that the sun is hot enough to vaporize dust if that dust is close enough to the sun. And as we said, once Parker gets closer, we'll really get some direct measurements of the dust density level once it's within the 7 million mile and then that 4 million mile region around the sun. The last result I want to talk about is one that involves high energy solar wind particles. We know, thanks to telescopes that we have here on Earth, that the solar wind and occasional solar flares can release these bursts of particles that travel up to 1 million miles per hour. We've detected them already. And we also know that they wreak havoc on our spacecrafts and our satellites when they hit us. The little video that you're watching in the bottom right there, that's the camera on the Solar and Heliospheric Observatory, or SOHO spacecraft. It's a spacecraft at the orbit of Earth that's designed to constantly take photographs of the sun. And when the spacecraft got hit by this very strong solar wind, you see that the white noise starts to go crazy. That's literally these particles from the solar wind overpowering the camera and causing some damage, causing it to go nuts, basically. So we want to understand, again, how these particles get moving so quickly, but we also want to know a bit more about what the solar wind is made of. Obviously, it's going to contain nuclei of hydrogen and helium because that's the main components of the sun, but the sun also has other elements in it. And if, let's say, a hydrogen atom struck our camera versus an iron atom striking our camera, the iron atom is much larger and heavier. It can cause a different type of damage than a simple hydrogen atom could. So we'd like to know about how these particles get traveling so quickly, and also what is the overall components of the solar wind, and can those heavy elements get traveling that fast, just like the hydrogen atoms do? So what has Parker taught us about all of this, about this really fast moving solar wind? Well, so far, Parker has experienced a couple strong solar wind events and flares. The ISIS instrument has detected heavy elements all the way up to iron in the solar wind, which is a little bit of a surprise. We didn't really expect these high energy events to contain these heavier elements, because as a heavier element, we imagine that it's harder to accelerate it to high speeds. The graph here is showing you days on the x-axis, so we're basically looking at information gleaned every day. And then this is intensity of different solar wind events. So don't worry so much about the units. Bigger numbers mean stronger intensity. That's all you really need to know. This graph is showing two solar wind events that occurred within a couple of days of each other. And this is event number one. The different colors are different energies for the particles that are hitting the different average energies for the particles that are hitting Parker. So you can see that around day 92.5, there was some lower energy particles hitting the detector. There were no heavy elements, meaning no iron or anything really much more than hydrogen or helium in this solar wind. But at this event down here, represented by the black, which happened about a day or two later, that was a bit of a higher energy event, and there were some heavier elements such as iron detected in that solar wind event. So this is just our first glimpse into what the solar wind is made of, and now we're trying to build connections of, when do we see the heavier elements released? Are there certain features on the sun that correlate when we would see these things in the solar wind? Do we expect to see heavy elements all the time in the solar wind? Does it only happen occasionally? This is one of those scenarios where, more answers is now bringing up more questions. But overall, it's really interesting to see that we've got our first bits of information about what the solar wind is really made of. And more information is definitely coming soon. All right, so you are all now experts on solar activity and space weather, and you're all up to date on what the Parker Solar Probe has been doing. Parker's going to continue its orbits around the Sun and Venus until it reaches that 4 million mile mark. It's going to continue to take data for at least 7 years, hopefully 10 years with a mission extension, and the fuel will run out shortly after that. Once the mission is over, the spacecraft will be turned towards the sun on purpose. We'll let most of the metal components melt, and the only thing that will be left of this spacecraft is a small carbon shield orbiting around the sun. I encourage you to keep an eye on the news cycles for some more updated information about Parker. I think we're going to get a lot more information from it very soon. And maybe in a couple of years, we'll do another talk, another update on the Parker Solar Probe, and hopefully have some answers to those big questions about the solar wind, the corona, and all the cool stuff that is happening with our sun.